Thank you for being here. I'm very excited to talk about collisions in isogeny graphs. The main purpose of this talk is to talk about a method that I describe in a paper that I put out earlier this year on arXiv. And the paper, if you want to have a look later, it's called Loops, Multi-Edges, and Collisions in Supersingular Isogeny Graphs. And it talks about exactly what you think it talks about based on the title. And all this work was done during my master's when I was at McGill with Eyal Goren as my supervisor. So what was the goal of this paper? So essentially, we wanted to describe a method that would allow anyone to study and find bounds for the total number of collisions in isogeny graphs. And when I say collisions, this is a very general notion because you can have very different kinds of collisions in these graphs. And why is that useful? It's because these collisions play an important role in post-quantum cryptography when it comes to supersingular isogeny graphs, and I'll describe these graphs on the next slide. So why is this method interesting? Well, other than being able to allow us to study collisions, one of the easy consequences of it is that it allows us to formalize very rigorously and very mathematically some statements that people in the community already know about these graphs, for example, about loops and multi-edges. So it's very useful to have these very rigorous and formal statements about them, not just have a very vague idea about it. So the methods that we use are based on Brent matrices and Hurwitz class numbers, and I'll explain more about this in the coming slides. So let me start with describing the supersingular isogeny graph, gamma PL. This is the notation that I use. And it's a graph, and the way to describe it is it's a bit mathematically involved, but basically the vertices of this graph are just supersingular elliptic curves up to isomorphism. And the edges of this graph are drawn in the following way. So for every supersingular elliptic curve on your graph, you look at all the subgroups of order L, and you draw an edge from E to E modulo C. And obviously here, we're sort of using the fact that E modulo C is also a supersingular elliptic curve, so that it's another vertex on the graph. So, and I guess an equivalent way of describing this graph is that the vertices are just supersingular J invariant that have to lie in FP squared, and the edges correspond to isogenies of degree L up to a certain equivalence relation, which is very easy to describe. So two isogeny will be equivalent if there exists an alpha, which is an automorphism such that we have this. And in practice, this sounds very fancy, but you know, in almost all the elliptic curves that you look at, this automorphism group is just going to be plus or minus 1. So this is not too difficult in practice. So now that we have this graph, and if you're not too comfortable with these supersingular isogeny graphs, you can just think of them as graphs, and I'll give you some properties about them. And these graphs are very nice because, first of all, we have a closed formula for the number of vertices on these graphs, and roughly it's about p over 12. But there is a specific formula to tell us exactly how many vertices we have. These graphs are sparse, they're regular, they're Ramanujan, which means that they're optimal expanders, which in very practical term means if you take a random walk on this graph and stop somewhere on some vertex, then this vertex, it's almost the same thing as if you chose it uniformly at random. So they're very nice graphs. And in the literature, in the community, most people know that these graphs have very few loops and multi-edges, but in a very vague and unprecise way. And the goal of that paper and this talk is to make this a bit more formal. Maybe I'll show you one of these graphs now, just so that you have an idea of what they look like. But actually, wait, let's go back one slide and say this before. So in practice, some mathematicians usually assume that P is 1 mod 12 to make sure that the graph is undirected. This is a very technical assumption, and it's not a big deal. I should also say that some cryptographers often assume that that P is not 1 modulo 12 for the exact opposite reason, and this would guarantee that the elliptic curve of J invariant 1728 is on the graph. But in practice, this is a very technical assumption, and it doesn't change anything deep about the graph. It's just so that the graph is undirected in my case, and it's just a bit simpler to talk about it. So the nice thing about this graph is you might have noticed that if I fix the prime P and vary the prime L, they will have the same set of vertices, but the edges will be different. So I could take two of these graphs and like superpose them in a compatible way, and I'll have two graphs on top of each other, just like in this photo. And I just made sure to draw the edges of one graph in one color and draw the edges of the other graph in a different color. So here we have two supersingular isogeny graphs on top of each other, one in blue, one in green. And for example, here, if I zoom in the green graph, we have here a double edge, which I also call a multi-edge. Here we have two loops, and here we have also two loops. So later in this talk, we'll investigate more this behavior of having multi-edges and loops. Okay, so now that I've talked about these graphs, I'm going to go over some background tools that we'll use, but I'll only mention what is useful for us, and we won't have to worry too much about the theoretical background that is used. So we use something called a Brent matrix. And the only thing you need to know about Brent matrices for here is that this Brent matrix is the adjacency matrix of this graph. And this is very useful because if you want to make statements about the graph, you can just look at the adjacency matrix and it should have the same amount of information. And this adjacency matrix, we know a lot about it because it's defined using some formula. And then depending on what you want to do, it might be easier to look at this matrix. So obviously you don't need to worry about all this math behind all of it. Another tool that we'll use is a Hurwitz class number. And also, again, you don't need to worry about how it's defined. You only need to know that it is essentially something that we can compute and that is bigger or equal to 0. And it's called the Hurwitz class number. And don't worry too much about all the number theory hidden behind this. Now that we have something called the Hurwitz class number, there is something else called the modified Hurwitz class number, which just to make things a bit more confusing. And the modified Hurwitz class number is just like the Hurwitz class number, except that there's this extra dependence on P. And the definition is a bit confusing, but basically, if you want to think about it in a very simple way, the modified Hurwitz class number is either 0 or it's the usual Hurwitz class number that we have. And the last case that you can have is it could be half of the Hurwitz class number that you can have. This last scenario here will never happen in cryptography, so you don't need to worry about it. So I guess if these two slides are a bit scary about Hurwitz class numbers and modified Hurwitz class number, the only thing you need to memorize is this inequality, which is very simple. Basically, the modified Hurwitz class number is between 0 and the Hurwitz class number. Okay. Now, we don't really need to know what these formulas actually mean in practice. You only need to know that we can go from Brent matrices to modified Hurwitz class numbers, and we can go from Hurwitz class numbers to this closed form formula. And obviously, if you want to see all the details, you can look at the paper, but here we just want to describe this method. And we're almost there. We're missing one last key of the puzzle, and it's a very intuitive thing to describe. So the concept that I'm going to say here basically is that a collision is the same thing as an endomorphism. And why? It's actually very simple. If you look at this picture, so we have a collision here. So you have a isogeny from E1 to E2, and you have another one from E1 to E2. And if you go from E1 to E2 using F, and then go back from E2 to E1 using the dual of G, you just get an endomorphism of E1. So and that's how you write it down. It's G dual composed with F. So every time you have a collision, oh, what happened?
Just a moment.
Is my screen still sharing?
No, not anymore.
Ah, I'll just, is it
Okay.
better now?
No. Okay.
Is it working now?
Yes, no, you can continue now.
Okay, so I was saying that every time you have a collision like this, it's the same thing as having an endomorphism. And now I can finally describe this method that I've been mentioning so often to bound the total number of collisions. So here's the method. And basically, we want to bound the total number of collisions. And as I just said on the previous slide, collisions amount to studying endomorphisms. So instead of bounding collisions, we'll bound endomorphisms. But what is an endomorphism? An endomorphism on the isogeny graph corresponds to starting at a vertex in the graph and then walking on the graph, and then finishing at the same starting point. So whenever you have something like that that starts somewhere and ends at the same starting point, it corresponds to an element on the trace, on the main diagonal of a power of the adjacency matrix. So we can go from endomorphisms to the traces of some Brent matrices. But now you might remember this formula from here that allows us to go from a trace of a Brent matrix to a sum of modified Hurwitz class numbers. So now I'll go from this step to that step, which is a sum of modified Hurwitz class numbers. But now you can remember this inequality that I told you to remember before that tells you that a modified Hurwitz class number is smaller than a normal Hurwitz class number. So we go from this to this, and this is an upper bound now. And finally, the problem becomes, can we find a formula for sums of Hurwitz class numbers? And we do have a formula, it's right here. And this is something that we can compute in practice very easily. So we end up with a final bound. So all of the theory that I've explained so far is to allow us to go from collisions and go through all these main mathematical steps and end up at a final answer that gives us a bound for the total number of collisions. And now let's do some example with all of this. One direct application is to loops. And I know loops are not actually collisions, but we have to start at something very simple to show you how it works, and then we'll do something harder. So the no-loop theorem basically tells us that this graph that is used in post-quantum cryptography has no loops if and only if this condition is satisfied. And what's nice here is that this condition only depends on the number of conditions here. There's only the number of them only depends on L. So if L is small, which is the case in cryptography, if L is 2, for example, you only have 3 conditions to check. And you can use some number theory to turn them into a different way of expressing them, and you get this. And you can look at my paper to see exactly how it's done. But the summary here is that the 2 supersingular isogeny graph has no loops if and only if we have this condition, which is very easy to check. And you can do the same thing for 3. And now that we found conditions to make sure that the graph has no loops, just because they're an easy consequence of this method that I described here, we also notice something in the proof of this theorem. And if you look at the proof, you notice that we can also find bounds for the total number of loops. And the bound is that for this supersingular isogeny graph, there's at most 2 L loops. And what's nice is that it doesn't depend on P. So, you know, if P is like 109, you have at most 4 loops. And if P is, I don't know, 10,009, you also have 4 loops at most, which is a very rigorous way of proving that you don't have that many loops in these graphs, especially if P is a prime with 400 bits and L is just the number 2. So this is the bound on the number of loops. You can do the same thing with multi-edges. And when I say multi-edges, we can look at this photo. It just means a double edge here. And we can do the same thing. And you can look at the paper for the specific bounds. I just didn't write them here because it would take some space. And now we can count how many redundant edges are in a graph. And redundant edges are exactly what you think they are. They're edges that if you remove them, then there's another one that's there anyways. And we can find bounds for those. And again, since L is small, this number of redundant edges is going to be tiny compared to the prime P. And now, this is something that I find is quite funny. So after writing down all the conditions for all the theorems that I've mentioned so far, you can compare the conditions that ensure that the graph has no multi-edges to the conditions that the graph has no loops. And you notice that one of these conditions is contained in the other. And that's just a funny coincidence. And basically, if this graph, the one where L equals to 3, has no multi-edges, then it's a direct consequence that it will have no loops, which in itself is quite funny because there shouldn't be any connection between multi-edges and loops. It just happens that if this graph has no multi-edges, then it will have no loops. And what's even funnier is if the graph gamma P3 has no multi-edges, then the graph gamma P2 is simple. And it's very funny because you shouldn't expect any relation between the graph gamma P3 and gamma P2. It just happens that they have this coincidence between them. So I think I've got 5 minutes left. So I'll try to, I should be fine, but then I'll take questions in the chat room instead at the end, hopefully.
Yes, maybe if you can use just 3 minutes, it will be perfect.
Yes, okay. So
Thank you.
so the final step here is we can compare, again, like before, the number of edges that two graphs have in common. And again, we can find a similar bound. And if you want to see more details, you can look at the paper and how I get this. But we can find a bound for how many edges they have in common, which is related to the edit distance of these two graphs. Finally, there's this notion of bi-root number that I introduced at the end of the paper, and it's a very general notion of measuring collisions. And it's very interesting because it's, I guess, the most general notion you can have of collisions between two graphs, and we find bounds for it. And I would refer you to the paper if you want to see all the intricacies of it. And if you want to read more on how this number of collisions is actually useful in practice, you can have a look at a paper that I've written with two co-authors, Federico Pintore and Mattia Veroni. And we use this method and we push it further to study the special soundness of the SIDH identification protocol, which is very much related to cryptography. And that's it. I hope you sort of got a flavor for like what these collisions will look like. And let me know if you have any questions.